Hello, Professor. We will introduce the topic is Numerical virtual flight simulation of quasi-cobra maneuver of a fighter aircraft. We are the second group. My name is Wen, and my student number is 108211313. This is the outline for this report. Introduction. Postal maneuvering has become a crucial factor evaluating the performance of modern fighter aircraft. This type of maneuver involves complex horizontally coupling multiphasic problems including aerodynamics, kinematics, flight control, and structural dynamics. Traditional control design methods based on linear assumption and inadequate for postal maneuvering, prompting the need for more accurate approach that consider unsteady effect. In recent years, virtual flight testing in wind tunnel, numerical virtual flight simulation, and flight testing of model aircraft have been developed to tackle this challenge. Among these methods, NVF simulation based on computational fluid dynamics and multiphasic coupling have gained prominence due to advancements in supercomputers and CFD algorithms. The arrest of the particular study has utilized an MVF simulation tool called Hyper Platform for Engineering and Research of Flows Numerical Virtual Flight Simulator to investigate the aerodynamic characteristic and unsteady effect of simplified quasi-cobra maneuver performed by a modern fighter aircraft. The research is conducted through four directions to enhance the understanding of dynamic lift at high angle of attack and lay the foundation for simulation more complex maneuver in the future. The numerical virtual flight simulator offers several advantages including cost effectiveness, enhanced safety through the simulation of various scenarios, flexibility for training of different aircraft models, and improved efficiency with real-time feedback. However, it may fall short providing a fully realistic flight experience compared to physical simulator and requires specific equipment to operate effectively. Thanks.
Hello, I'm Ken. So I'm gonna talk about some common use method in computational fluid dynamics. So the first one is C6DOF simulation. So in the beginning, as you can see the flow chart, we need to generate the fluid field data. And how does it work? I will show you in the next page. And keep going. The data will send into the 6DOF solver and with the input of control command, which may be like the temperature or pressure or something. And after the CFD, RFB, RBD, FCS coupling, and we will get the desired simulation data. It could be the pressure distribution of the object or the aerodynamic force. And next is the computational model and the dynamic offset grid. Once we have the data, input the parameters and put the object data into the software, the simulation gets started. Sounds easy, right? But how does it work? So in some ways we can see simulation always needs a lot of calculations. So in the other hand, it will take a lot of time. So there is two types of the grid generation. One is structured grid. It have higher generation rate and the data structure is simple. But in this case, our simulation object is a plane. So a plane is a very complex structure. So for the more complex object, the unstructured grid is more suitable than the structured grid. So using the unstructured grid can make the simulation data more precisely.
A. The Case 1 static state simulation. To determine the static aerodynamic characteristics of the aircraft, the paper first studied the static state at different angles of stack. In this case, the incoming flow conditions are the Mach number Mach 0.6, the renamed number 1 plus 9A for 107, the angle of attack alpha 0 to 45 dash, alpha 5 dash, the angle of side safe beta 0 dash, and the elevator deflection angle E 0 dash. First of all, for static state simulation, a great convergence study of the aircraft force span model is carried out to determine the proper size of the grid. We consider three sets of grids with different grid densities. The detailed information is shown in Table 1. Steady range simulations are carried out on these three sets of grids. A finger flow depicts the radiodynamic coefficients of the steady state at different angles of attack, in which the experimental data from a transonic wind tunnel are also shown. The results show the curves of the metal and foam grade almost coincide with each other, while result in the cross grade showing a small degree of difference. To balance the accuracy and the efficiency of numerical simulation, we therefore adopt the metal grade as our benchmark grade. Meanwhile, for the benchmark metal grade, the depth of charge coefficient agree well with experimental data, but there are some difference between the moment coefficients. The discrepancy issue of the moment coefficient was also encountered in previous studies. This may imply that the current second-order range simulations are incapable of capturing the moments of complex geometries in highly separated form, or in this paper, because of the effects of the support system in the wind tunnel and the neglect of the assembly pylons during the geometry simplification process. Finger flow shows that the phase coefficient vary slightly with the angle of attack before it approached 25 dash. The approximate stall point is alpha 35 dash, and the corresponding life coefficient is greater than 2. When alpha is greater than the stall point, the life coefficient decreases very slowly with alpha increasing. which indicates good aerodynamic stall characteristic of the aircraft, the high alpha. Besides, the drag coefficient increases monotonously as alpha increases, which is obvious because the wind was aerial. As a result of the pressure drop increase with alpha increasing. For the pitch moment coefficient, the aircraft is stable since the moment coefficient is negative for a positive angle of attack. Also, a fast regression can be found on the moment coefficient curve for alpha smaller than 50 dash, which indicates that the coupling between the aircraft and its elevators is not obvious before this point, and therefore the control surface efficiency could be very high. When alpha more than 50 dash, the moment coefficient increase almost linear with the angle of attack.
So we adopt the Q criterion to identify the vortices. Figure 5 shows the iso surface of Q equal 1 at 6 typical angles of attack. As you can see, there are different alpha. The formation and the breakdown of the vortices can be discovered. However, due to the grid resolution and the limitation in the dissipation of the RANS model, the subscale structure of the vortices cannot be resolved. Therefore, among the advanced models nowadays, DES is the most feasible method at the current stage. This is figure 6 and is about slice position on the wall. We will take a look about the ratio on figure 7. Now look at figure 7 shows the CP distribution at 6 cross slices as shown in figure 6 on the solid wall at different angle of attack. I would like to emphasize ratio 0.4 and ratio 0.6. For slice ratio 0.4, the peaks at a 45 degree are even lower than the peak at a 25 degree. This indicates the strain wave vortex is starting to break down at ratio 0.4 for a 45 degree. The same phenomenon occurs at ratio 0.6 for a 35 degree, which indicates that the main wind vortex is breaking down at ratio 0.6 in this angle of attack. Follow the same rule. We can easily conclude these 2 points. 1. The vortex breakdown location is moving forward as the angle of attack increase. 2. The stall point and the maximum lift coefficient are diminished by the breakdown of the main wind vortex.
My name is Jason. Puppy is a 1DOF vortex pitch R motion around the fighter's mass center. The grid is rotated with the aircraft as an entire rigid body in this case. The nonlinear pitch R motion can be defined as follows. Table 2 shows we consider to reduce frequencies are 3 times state size. Figure A shows the variation of angular velocity and the angle of attack with non-dimensional time for k equals 0.05. Figure 9 shows the comparison of aerodynamic force and the moment coefficient for different time state size when k equals 0.05. The curves show very good agreement for the three choose time state size. It seems that the unsteady numerical simulation results are not sensitive to the time state size. Figure 10 shows the comparison of aerodynamic forces and the moment of the pitch R process and the steady state. The dynamic forces and the moment are larger at the same angle of attack when the reduced frequency increases, especially at a higher reduced frequency. Figure 11 shows the comparison of pressure coefficient distributions of steady state and the dynamic pitch R at alpha 35 equals deg for slices 0.1 to 0.5. The suction peaks on the leeward side are lower than those of steady state, and the windward surface pressure is smaller for dynamic pitch R with the larger reduced frequency. For 0.6 to 0.9 slices located behind the rotation axis, the result is the opposite. The reason for this phenomenon is that the effective angle of attack is changed due to the dynamic motion of the aircraft. As shown in Figure 12a, the effective angle of attack before the rotation axis is smaller than its actual angle of attack, which leads to smaller windward side pressure, smaller vortex strength, and a lower suction peak. By contrast, the effective angle of attack behind the rotation axis is larger than its actual angle of attack. As Figure 12b shows, this leads to opposite result.
In this slide, I will introduce the case 3. One dove pitch R by single-channel open-loop control of the elevators. In this session, the author designed a single-channel open-loop cosine function control load of the elevator is defined in the equation 3. Delta is deflection angle of the two elevators. K is reduce the frequency, which set to be 0.05 in this section. The control load is sketched in Figure 13, and the parameters are listed in the Table 3, and the author would like to simulate more physical time. A relative closest time step is chosen in the case. The dimensional time step in 0.0031 seconds, which is very close to but still smaller than the reference time. The maximum elevator deflection angle is delta maxima is 50 degrees at 0.31 seconds and remain constant afterward. In this slide, I will introduce the Figure 14. As you can see, the time history of the open loop control pitch R process and the pitch angle theta is equal to the angle of attack alpha. To analyze the process more carefully, the table 4 lists 5 typical snapshots during the pitch R process. It contains the snapshot that illustrate the behavior of the aircraft at different times during the simulation. In this slide, I will introduce the Figure 15. And in this figure, It shows the Q1 ISO surface contour or typical snapshot, which demonstrate the generation and the breakdown of the straight wing vortex, the main wings vortex sheet, and the wingtip vortex with the pitch angle increasing. In this slide, I will introduce the figure 16. It shows the pressure coefficient on the wings at a time equal to 0.85 seconds. It illustrates that the section force peak decrease at the slice x divided by L equal to 0.3 and become flat at x divided by L equal to 0.6, which indicates vortex broke down on the main wing and lift style around this pitch angle.
Next, we describe the case for 3DOF quasi-cobra maneuvering. They use the NVF simulator presented in second section to simulate a simplified 3DOF quasi-cobra maneuver, and the initial flow conditions are the same as in third section. Then the initial constant thrust model is introduced to balance the drag force when alpha equals 1.8 degree and provide a small extra acceleration in x direction. Besides, the initial elevator deflection angle delta E is set to be 0. And then design a cosine function open loop controller as shown in this. And the controller is sketched in figure 17. Open loop cosine function controller is enough to make sure the aircraft accomplish the expected maneuver. Authors introduced two types of simple thrust model, including constant thrust model and vector thrust model, which change the direction and the magnitude of the thrust at 0.93 seconds. Figure 19 depicts the time history of maneuvering process. By fuselage growth, the total pitch of moments decrease. At this time, the pitch moment changes its direction, and the aircraft's pitch of angular velocity begins to decelerate. Until this time, the aircraft reaches its maximal pitch angle. At 0.93 seconds, the difference between the two models are increased gradually, and Model 1 drops more slowly than Model 2 since there is no extra pitch down moment produced by the vector thrust. Model 2 is similar to the Cobra maneuvering. Figure 20 shows the Q equal 1 isosurface contour of 9 typical snapshots of thrust Model 2. Figure 21 shows the trajectories. The total relative velocity between the aircraft and the phase string is Mach number 0.6, so that the aircraft will move forward in the x direction. The methods in this work are applicable to the simulation for true Cobra maneuver.
In a conclusion, to study the postal maneuverability of the fighter numerically, the quasi-cobra maneuver of a modern aircraft is simulated using an NVL simulator. Through the simulation, the static aerodynamic characteristics of the aircraft are obtained, and the understanding of the mechanism of the high lift at a large angle of attack is deepened. By applying appropriate deflection command to the elevator through open-loop flight control loop, the fighter can pitch up to the high angle of attack from the cruising state, and then pitch down quickly. Although the maximum pitch angle is much smaller than 90 degrees, the maneuvering process is similar to the Cobra maneuver. Even the RANS simulation in the paper are not necessarily highly accurate. The plenary application in this work demonstrate the potential of the NVF simulator for the simulation of realistic postal maneuver, which is very useful for modern fighter design. NVF results also need to be validated with wind tunnel experiment and model flight testing. For your attention.